The last 2 weeks we had to slightly alter the schedule by not doing anything at all. But that paid off. We're back and I'm sitting in my new office, which isn't soundproofed yet, so the echoes might still be pretty bad. But at least I have my new desk ready. I can actually stand in front of the mic instead of the awkward positioning I had before. But those are details that are not important. In our last lesson, we had to look at a way to create our own data types using the keyword struct, which was also the first time we had a more abstract look at code. Instead of just writing out instructions that the computer can perform one by one, we used code to define data in a way, to give a structure, no pun intended, for the code to work with. So we work on a more abstract level. Instead of just telling the computer what to do, we gave the computer information on how it can do things. And instead of looking at the homework, we'll start right away. For today, we're gonna make first a simple... this doesn't look right. Great. Great. We're back to the beginning, it seems. My setup is... there we go. That looks better. We're gonna start with a simple struct. And we're gonna do an example that's pretty classic. So first, we still use the keyword struct to tell the system that we're creating a new struct, and then we give it a name. And that's gonna be point. Because geometry structures are pretty classic. I'm not gonna say trope, but classic way to introduce custom data types. And I cannot... What's going on? Let's just try this again. Okay, that worked. So we're gonna make a new struct, then curly brackets. Still cannot write curly brackets. Let's leave it at that. And this point is gonna be referencing a point on a 2D grid. So we can just accept integer values, that's gonna be fine for us. And this is gonna be integer x for the x coordinate and an integer y for the y coordinate. And then we're also gonna introduce a constructor. And that's just gonna be point. And we're gonna give it one integer x and one integer y. Like that. Again, curly brackets. And then we're gonna set x to x, uppercase x to lowercase x, and y to y. Close it up. Close it up. Oh, better than nothing? No, it's not better than nothing. Okay, let's try. I give up. I should not be attempting to write this stuff out by hand. There are things that are not meant to be, and my handwriting's forever cursed. In any case, this is one part of our code. This is where we just create the definitions for our data, the abstract part, and then we have another part of our code that actually does something. And in this other part, we can now create a new point A, and we have to tell the system now that it has to construct this more complex part, more complex point. So we use the keyword new to indicate that we're calling a very special method of the structure point. And it's gonna receive two values from us. And let's just go with 1, 2, like that. And that's it. We now have a new structure point, and we use that to create a variable that stores the point that stored the data. And just a refresher, Let's do that up here. If we reimagine our table, so up here we just had type int. This one was x, this one was y, and the value, well, whatever we store it there. But down here we would have our large table. Let's make it a bit more skewed to the side here. So we have point A, but this in itself now has this entire table. So this is again just int x1 should be big enough. Not bad. So using our old analogy with the table for the different variables, this is the general structure we outlined for what points are. So whenever we store a point, well, we don't have a single value in here, but we have an entirely new table which in itself has individual values and can have, again, more tables inside if we use more complex types instead of integers, for example. Yeah, this is a simple example, just a reminder. Let's expand on this a bit, because I want to demonstrate something, and we'll have to create 2 more structs for that. This code is still relevant, so we're going to keep this structure point around. I'm going to create a new structure though, 2 new structures. I'm going to put them side by side, I think, to save on space. The first one is struct player, because we're going to make this a bit more interesting. I figured I'd grab your attention a bit better with gaming analogies, as if we were creating a game. And a player is going to have, at least in this scenario, 1 point for their location. And they're gonna have 1 integer health. And then we're gonna make constructor again, player, and they're gonna get 1 point maybe position would be better than location, but use it already. And we're not gonna pass on health because we just wanted to start with 100 at all times. So location, just notice this is hard to distinguish. Uppercase, like that. Location equals location, and health, we're just gonna always start with 100. Yeah, and the side by side doesn't work, we're too wide for that. But this is another structure now that we can use. Let's go back. We can, for example, right now player P. Actually, that looks like an uppercase because it is kind of an uppercase. Let's use a lowercase p. It's not writing properly. It's weird. I'm putting down my pen, but it's writing offset to the pen tip. This is a bit... Probably have to switch the tip out, but not during the stream. Nope. Okay, I'm getting used to it. Whatever. This is gonna be a new player. And we're gonna pass in A, which we already have. And luckily that just barely fits in here. So now we have a new player. Let's add him here. And it's player P. And this is where things get a bit more tricky, because now we have the table internally for the player, which was the location, dot dot dot. Wait, forgot to write that out. That was first. How do we do this? It's gonna be a bit small if I write everything out now. Nah, let's try it. So we have point. What do we want? Location. Dot dot dot. That in of itself has another int x on int wide. Okay, yeah, this is getting ridiculously small, but I think you get the idea of what's happening in here. And we have the integer health, which is 100. So yeah, it gets a bit ridiculous, so I'm not gonna bother with writing out these tables and tables and tables anymore, but this is what we have in memory. Now let's create the second struct, because we need an enemy, and that's gonna be monster. That almost looks good. Almost. Let's keep it like that. Bit misshapen, fitting for the monster. And the monster is also gonna have a point for location. Uppercase, location. And the monster is gonna have power. How strong are they? And then we're gonna make constructor method, which is going to get point. I'm just gonna make it shorter here with an L. And an integer P for power. Because this time we want to specify the power ahead of time. Boss monsters can be in different strength. Is it a boss monster or is it just a little mob in the beginning of the dungeon? And then we can store that. Location. Just gleich L and power is equal to P. And let's keep it at that for now. And we're creating the monster. Same as we did the other things. Monster M. New monster. Just gonna continue writing down here. Actually, let's move it further to the side. Here. So we just continue on the new line. And actually, no, that's fine. Let's leave it there. That was fine. And we're creating a new point now, which we're gonna do in one go. We're not bothering with storing that in a different variable, which is perfectly valid. Still having the offset in the pen. Point. This one's gonna be located at 5, 5, 5. Whatever, and it's gonna have a power of 2. Like that. And now we created a monster as well. So we have a monster M, and then we have the whole table with table. Basically the same as player. Well, it's the same layout. it just has a slightly different meaning, because in one case it means health, and the other it means power, but it's still a point and an integer. So they are just, the layout in memory is basically the same. They just have different meanings depending on what it is. And if we were smart, we could actually use one single struct and just reuse it in different ways. But that's not what we are about. Not today. And now we're gonna do something with all of these. And to do that, just gonna break this up here and make ... because we're continuing this struct monster. So this is still struct monster. As heads up, these two forward slashes, which I should probably need proper spacing since I'm doing that everywhere else. These are a way to indicate comments. So I can write these out in actual code and the computer would just ignore everything I write in there. So I can make little notes and little hints everywhere. Just to keep in style, I'm putting that in here as well. So just imagine I'm continuing to write down here. Right, this is where we continue. And what we're going to do now is we write a method. A very special method that is unique to a monster. Well, not unique to a monster, but that is intended to be used on a monster with a monster. So that's why we're adding it to the struct itself and not somewhere else in our code. So, okay, sorry, the music's kind of distracting right now. Let's switch to the next one. Whatever. There are certain tracks in here that just stand out too much and I'm so distracted. I associate certain memories with these songs, even though it's just a mega playlist of... Okay, doesn't matter. Oh, by the way, if you don't know, Crinkles, music, huge selection. Like, this soundtrack is from a couple of years back. I still have the files, that's why I use them, but... And I paid them, just to be fair. I did donate, so it's not like I'm getting free music here. If you like the music, maybe go there and send them some money or some love. Made a lot of new albums. If you're looking for background music. Getting sidetracked. A special method. So what this method is going to do is it's not going to give us anything back. We declare it as a void. So we write a method, but it's not going to return any values to us. And we have to declare that it's not returning anything to us by explicitly telling it void. And this method is going to be called a tag. And this looks like an uppercase K because it is an uppercase K. Oh, that's better. Whatever. And it's going to get a player. We're just gonna shortcut it with another P here. And the way it's going to work now is our monster will charge at the player and hit the player with as much damage as it has power. Simple enough, right? So that means we have to do two things. First, the monster has to change its position because we now change from wherever the monster was placed. We charge towards the player and have to now be at the position of the player. But at the same time, we also have to change the player themselves because they now have less health. So let's first take care of the positioning. The monster charges towards the player, so we have to take the position of the player and store that in the monster. So position in both cases was just called location. So what we can do is first we refer to our own location, which is available because we're inside the monster themselves. remember, this method is written inside the struct, not outside, so we can use all the variables we've declared in here, location and power, as if they were just declared inside this method itself. Like, this is just one scope down. So location, and we're just gonna set this value directly to the value the player has. Same location, and to do that, as a reminder, we refer to the player in question, P, and use the dot operator, so just a simple dot, and then we specify what part of this player we want. So if we go back, we want this location from the player, and if we go back a bit further, remember, dot operator just means we go look for player, P, in both cases now, and then dot operator means in that value now look for something else, another variable name within this table. And then we can go even further with point and even go deeper into that table. So in practice, we can do location. Like that. And our job is done. Because now we just simply copy the entire value that's stored in the player's location and put that into the monster's location. We could, using dot operator, also refer to specific values of location, like x. Now we refer to the integer value of x that is stored in the location inside the player P. So dot operations always just specify what to do with an existing object that we have. Specific value. But yeah, player location is copied towards the monster location. The monster is now at the same place as the player. Now we have to lower the health of the player. And so we just change it P for the player dot health, because we want to specify, but to change just one part of the player's data, not the entire player. Health. And we set this to p.health minus power. And again, power is just the variable we declared inside the monster, so we can just use this as is without any dot operations because we are already inside the monster. That sounds wrong. Yeah, like that. Of course, we can also use the shortcut now. Instead of just equals, just use minus equals just power. Like that. And the method is done. And we can close the struct in there. We're done. So when I go to our code, again, to the actual code we started with, if it would let me. Thank you. We can now call m dot, because we're making a call. Again, dot operation. This time not for a variable inside the monster, but for a method inside monster. Attack. And attack received a player from us, so P. And that's it. Now the monster, which was previously located at 5,5, will now be located at 1,2. So if we look at the table here, the data, the monster's data was previously 5,5 in terms of position or location, and now it will be 1,2, same as our original point, which was the same value that we copied into the player, which is what we copied over to the monster. However, if we check the player's health, it will still be 100. What is happening here? If we were to try this, the player's health would still be 100, even though the monster attacked the player. And our code specifically reduced the health by power, which we know was 2. So we should be at a health of 898. What could be the issue? The answer is we changed the health of a different player. Because once this method was called, remember the call stack, we have first our original code, where we actually, let's go back to the code. So we have our call stack. So this table is actually here. In our call stack, in the stack in general, a special region in memory. And once we make this call here to this method, we reserve space on the stack below our original memory, which all our data is in. And we fill the data with some information we already know, like the return address. So we know this is where we go back to once the method is done. We talked about that. But we will also present the method with the data we got from up here, from our call stack, because we made the call using the variable p. So we will copy the value from p down here into this new part in this stack. And that means we copied this player p down here. We made a copy of it. So the entire player with a health at 100 and at position 1-1 exists now twice in this stack. Once up here, where we wrote our original code, and once down here, where we currently run the attack method. So when we change health, we're changing it down here, not up here. This up here is our p. This down here is another variable p that's exclusive to this method attack. And once the method returns, this entire part of the stack is just deleted, ignored. It's gone. So the player that we actually changed was down here and it's gone now. And the original player, p, that we wanted to change is still the same as it was before. To change that, we have two options. Well, I mean, technically we have more options, but you know two options so far. The first one would be to go to our method and change this from void to player. Let me just skip that in here a bit and then make that return p like that. So now we get a copy of our original player and change it, and then return the changed copy of the original player. And then we can, that was my pen, then we can move all this to the side and just say p is now equal to m.attack. And now we get the copy of the change player and overwrite p with this change player. So the original p in here is gone and we overwrite it with the copy. Well, technically, this will also be a copy of the copy, because in the call stack, once we return the data, we're going to copy it back up. So this is technically a copy of a copy, but that doesn't really mean much in the computer, because 100 is 100 no matter how many times you copy it. There's no original in that sense. Everything is a perfect copy unless something broke horribly. That's a different issue. But this is one way to go about it. Certainly a bit more annoying, but actually might be beneficial to you if you don't want to lose the original data. Maybe you want to compare it to something. There are always certain scenarios in which you do not want the original to be changed, so having a copy and changing only the copy is preferable. In our case, however, we don't care about the original data, we want to use the new data. And that leaves us with another option. Let's move this back. m.attack. Have to space it out a bit more. Remember the keyword ref. That's the other option we have. We now go to our original code here. We have to once more change this back to void and no return. And we have to change this now to also explicitly tell it that we want a reference. So this is ref player P. The rest of the code can stay as is. But what happens now is, when we run our code, it will not actually copy the value of P, going back to the call stack. So hard separation here, that's our table. And so on. We don't copy it down for the method call. We just pass down a reference. So instead of actually having a full copy with the full table and whatnot in here, we just give it a simple indication, hey, if you need to do anything with that value, it's up here in the memory. We can use it down here in our method, but it refers to a different part of the memory, different part on the call stack. And so when we change it, we actually change it up here, where our original player is actually stored. So when the method returns, and this part down here is completely gone, the changes that we made were up here and are still there. So this player now will have different health of... can I remove this? Careful. Okay, that didn't work so well, but this will now be 98. So the ref keyword is useful not just for allowing a method to return more values than just one, because usually a method only has one return value. It also helps us structure our code a bit differently, because logically we want to change this variable p, even though we are changing it in an entirely different part of our code, in a separate method that doesn't have any direct connection to this code here. So that's also a way to make more use of the ref keyword. But there's one thing that we can't do with ref. Well, for one, I have to write a bit more, but that might be fine. Right now, I'm copying over location to location. I'm copying the location, the value of the location for the player to the variable that stores the location for the monster, which is fine. They both have a location, so I'm just copying it over. So now in our stack, in our data, we have the location 1, 2, once on the point, and we have it once for the player, and we have it once for the monster. The exact same values are in the memory 3 times. For one, that's a bit of a waste, especially the original point is not needed anymore. We only used that initially to create the player, but other than that, we can get rid of it and free some memory, in theory. But more than that, let's say I want to change position of the player now. P.location x plus equals 2. This line advances the player's location along the x-axis by 2 units. But what if the monster was supposed to follow the player? Maybe it's stuck to the player. Imagine a slime that gets stuck on some part of the equipment and is now giving permanent debuffs or whatnot. Whenever we do this change, we also need to change the monster's location. We need to update it exactly the same way. Location.x plus equals 2. Every time we change one, we have to change the other. Perfectly valid, and I know I'm straining the scenario a bit here, but wouldn't it be great if changing this x would also change this x here? Basically, wouldn't it be great if the location the monster had was exactly the same in-memory location as the player's? I'm beginning to feel like the location name was not wisely chosen. Any case, if this was the same memory location for the monster's location, seriously, I have to change the name. Maybe next time I hold this lesson. Then any change we make here would also update the monster's location, because it's the exact same value in memory they both refer to. You can't do that with ref. The ref keyword is exclusive to methods to indicate that a certain argument is not passed on by value. We don't copy the actual data of the variable, but by reference. We only tell the system you can find the original data somewhere else in memory. You can maybe write that down somewhere. These are two common phrases: call by value, call by reference. Call by value is we just give you, where u is a method, we give you all the data you need and you can just use it. Call by reference is we're giving you an address and you can look that data up there yourself. Both have their advantages and disadvantages. It very much depends on what you need at the exact moment. So you will use both when programming a lot. And sometimes these can cause unwanted effects. You could say side effects, especially something with ref. Again, earlier, the first example, we had a copy of player in here. So whatever we did to this player P did not affect our original player. In our case, we wanted it to change. So we changed it to ref. So now whenever we do something with player here, it affects the original player because it's one of the same location in memory. What if we didn't want to change it? What if we wanted a theoretical? What might happen if a player would be attacked by the monster and try to get the result of that? We didn't want to actually affect the original player. In that case, a reference is an issue. That happens in a lot of cases. You just have to be aware of what to use when. Back to the topic. Right now, we don't have a convenient method of just aligning these two memory locations. We only have a method to sort of align memory locations using the ref keyword and methods. What we can do, however, is sort of marking a struct, the entire struct, as always use references. So that whenever I pass it on as an argument, like here, it would just automatically assume this is a reference, not a value. We make a call by reference, even if I leave out the reference keyword. And to do that, let's leave it like this. We're going back to player. And player is not going to be a struct anymore. We're going to use a different keyword. And this different keyword is class. And we'll leave the rest of the code exactly as it is. This is now like a structure, but that's always using call by reference. Now when I refer to player here, I'm not referring to actual data. We don't get any actual data. We get a reference to another part of the memory where the actual data is stored without a ref keyword. That also means we don't have to add the... Please, let me move back a few pages. Like that. We also don't have to include the ref keyword here anymore, because the computer knows player is inherently reference-based. It's no longer a value here in memory. Player P is inherently just an address in memory where we can find a table with the data. We don't know what address. We don't know the actual value. We don't know how the computer is going to find it. But we know it's there. The question that you should be asking now is, where in our stack is the data now? If we only have a reference, and that reference is already used up here where we created the player, where's the data now? If it's not in here in this table, it's not in our stack up here. And it's also not down here in the next part of the stack where the attack method is happening. Where's the data? And that's where the, I guess, titular heap comes in place. If we look at our entire memory in the computer, at least the memory that you can use for your code, this looks as ugly as I imagined it. Which is good for me, not good for you. Let's make it a bit cleaner. Let's at least pretend I can draw. Like that. We have two major parts here. Let's say we have three. There is a certain part of memory that we're not going to discuss. That's needed for your program to run, for the computer to use your program. There's a bit of data in here that we don't care about right now. The most memory that you're going to use is either the stack, which you've already seen, or it's going to be the heap, which we're discussing now. The stack is just, okay, we start at this address and we're slowly working our way down as we need it. So we have a method, we have some variables in here with our tables and data and whatnot, and then we call another method from that method, and that means we reserve some more space below. Then some more space from there for every method we call. And every time we return from a method, we just remove that part and go back in the stack to the next one up top. So it's always growing downwards and then always shrinking backwards up. So there's always going to be this free space in here that's not going to be used, that we can reserve as we need it as we go down here and grow our call stack. The more methods you call in a row, the larger the stack will go, and as you return methods, it will shrink back up and use less memory. And that means, of course, at some point, if you call too many methods in a row, you will run out of space in here. And that's a stack overflow. Now you know where that name comes from for a certain website. There's another part of memory that starts down here then, but this one is not organized in any real way. This is just free memory that's free to use for whatever you want. Technically, you can even specifically use commands to say, I want to reserve memory in here. And the computer will just say, okay, here's a certain part of memory that is not going to be used for anything else. This is now free for all for you. Or whoever you share this memory with, which you can do in theory. But usually the computer will try to look in the heap, see where data is reserved and where data is free, down here and up here. And when you need any memory, or when the computer itself needs memory, it will just say, okay, I'm reserving this space up here maybe. And then when you need more space, okay, I'm just gonna reserve space up here. It will try to align it with other parts of reserved memory so that these blocks of free memory stay as large as they can. Imagine you reserve some space here, and maybe some space there. All these very thin slivers of just a bit of memory, and then at some point you need to reserve one large chunk of memory that would not work anymore. So instead, you're just trying to align everything close to each other and keeping the free memory parts as free as they can be, so that when you need a large chunk of memory in one go, the computer can give it to you, or can use it itself. That's the heap. It's just a big region of memory that's very unorganized, that the computer tries to keep organized, but it just can't keep up all the time. So there's always a bit of chaos in here. And this heap can also run out of memory. And that's just usually what you have with an out of memory exception. If you ever seen one of those, that just means, hey, you had no more space on heap left. Doesn't mean there's no space on heap. It could also mean there is enough memory free inside the heap collectively, but it's just so scattered that you can't reserve this continuous chunk of memory that you need. It's a bit similar to defragmentation, if you remember that from hard disks. If you ever had to defragment your hard drive, that was also just about organizing memory so blocks of memory that belong to each other stay together, and blocks of memory that aren't used for anything are collectively put in another part that's... What just happened? Oh boy, that scared me. Ooh. It's good, it's good. Just some scables doing spooky stuff. We're good. Everything is live. I'm not electrified. I think? No, I'm alive. And we're alive. Good, then just let's continue the stream and I will look at that later. Let's just stay away from that cable a bit. It's not a fire hazard, so not... should be? Maybe if I look suspiciously enough for long enough, it will just fix itself. It's not doing anything anymore, so it might work. So yeah, that's the heap. And when we go back to our code, when we create a new variable for struct, it's not letting me move back and forth. When we reserve a memory for a struct like point, we will reserve exactly as much space as that struct needs in the stack and then fill it with all the values directly. When we create a class, construct a new class like player, we will only reserve enough space to fit one address. This changes depending on the computer architecture and your process architecture. Rule of thumb, if you're running a 32-bit process, this address will be 32 bits. If you're running a 64-bit process, this will be 64 bits. Because these refer to the space you have for addressing memory. That's what the 64 and 32 or 8-bit roughly are about. How much memory can you address in one go? And that's exactly what these are, these references. They are addresses to memory. So if you have a large memory, you need a lot of space to store potential addresses in that memory. If you can only count up to 10 and you have 20 houses in your street, then, well, you have a problem. The letter won't arrive at house number 11 because the postman doesn't know what 11 is. So instead, when we create new player, it will reserve space for one reference, 32-bit, 64-bit usually. And then it will at the same time go to our heap and try to find a spot that is big enough to fit exactly one player, as if it was trying to fit in a struct. Because the player, even though it's not a struct, it still has the same size. Well, kind of. Technically this is a bit different, but let's not get into that. It still has the same size constraints. It still needs to fit one point, which itself is 2 integers, and it needs to fit the health, which is also an integer. So it needs to have enough space somewhere in the heap for 3 integers, roughly. And it will try to look for a free spot somewhere, depending on what strategy it's going to use. It's probably just reserving some space right up here, the first free entry, and it will then use that address wherever that is and put that back into the stack. So the first address is going to be put back into the stack where we actually store our variable p for the player. And when we call the method here, attack, and we pass on player, what we actually pass on is the reference. Because this is, just like with a struct, this is not a ref. So we are actually copying data. We're not telling the method, hey, refer to this other part in memory. Please let me... the gestures on this thing. I'm swiping, I'm swiping. It's not detecting my swipe. It's annoying. I could have come up with stronger words, but I'd rather not say them. But I tend to say annoying a lot. I have to find better words that are still okay. Hey guys, when I call attack, we're still copying part of our memory over. So this value, this address value, whatever address that is at that point, memory address, is going to be copied over to this part in memory. This can be still used as a ref. We can use the keyword ref here and in the method declaration itself. In which case we still would just say, hey, if you need p, go up here. That means we have a reference to this reference. So if you use the ref keyword with a type of data that's not a struct but a class, then you're basically using a reference to a reference, which itself might contain other references. It's references all the way down. Yeah, so we copy over the address. So the same address is available in the attack method that's also used in this code here. And then in the attack method, when we refer to p, the system knows this is an address in memory in the heap, and that's where I'm gonna find the integer health. Still exactly the same way everything works, except the data is no longer found in the stack, and instead it's in the heap. And whenever we use the data or refer to it, what we actually use is the address where we find the full player data. And all it takes is just a different keyword. It's either struct, to always make sure monster is just a straight up value. A sequence of ones and zeros in memory that we're always just gonna copy over. And a class is reserve some space in the heap and always use the address in memory where we've put the data and give that around. It's the difference between I'm giving you a copy of a monster encyclopedia, or I give you the name of the book and tell you where you can find it in the library. So I make a full copy of a book, or just give you the information where in the library you can find it to look it up yourself. That also means, of course, again, the issue of we have one location in memory that everyone is changing. So if you're changing it, it's changed for everyone else as well. If you rip a page out of that book, no one else will have that page either. Whereas here you make a full copy. So if you make any changes to your book, or to this monster, it's only going to affect you, and everybody else who has a copy of that book will still have the original copy. Or whatever version they have after they made changes themselves, which you don't know anything about. Both are useful properties to have. Both structs and classes are used a lot. There are other data types that are in the end just special versions of class and struct. So at first at least focus on these two. Just a side note, because classes have some other properties that are going to be very important soon, they tend to be used more. Structs are still kind of a special case, and they have some limits, but they are very useful to know. And they are the easier one to understand, I think. That's why I started with it. For now, just imagine class. You want to use a reference to some data that everyone is going to share. Struct, here's some data that only I know and someone else just gets copies of it. Going back to the original problem, point. What if we want to change point? Well, we're just gonna flip this around. This is gonna be a class now. And so we create a new point, which is no longer in the table directly. Again, this is just another reference to some location in memory, somewhere in our heap. And when I pass it on to player, player is also gonna have just this reference. So that means that this location for player that is stored somewhere in the heap is itself just a reference to yet another point in the heap. Then we create a new monster, which monster is still a struct, which is full version here in the table, in the stack, all the data. Except point, of course, is a class, not a struct. So in this case, the point will not be part of the table here. It's also just, again, a reference to somewhere in the heap. And that means, finally, this location here and this location here is both not directly a value, but just an address to somewhere else in memory. So when I copy player.location into monster.location, what I'm copying over here, what I'm assigning to this variable is the address in memory, the reference, not the actual data. So we're not copying the data, we're copying the address. So our code will still work. The monster, after attack is called, will have the same location as player. The monster will now also be at position 1, 2. And the player will have a health of 98. What changes now that we change location for the player, we change the same memory address that is also used by the monster. So we're also changing the position of the monster. Of course, now we have an issue where if the monster is supposed to leave the player alone and go somewhere else, we have to actually create a new point. So we reserve some new space on heap, so the monster can have its own independent location. Because right now they use the same memory location, which can only store one location. Seriously, the name location was a bad choice. Well, guess we all learned something today. Alright, I think that's quite a lot. So we're not going to do too much more. One more thing on heap and organizing the heap. The monster had a location of 5, 5 and the player location of 1, 2. And both were just parts of the heap that we had location, that we had an address for. So somewhere in the heap we stored 5, 5 and 1, 2. And now we just said the monster should forget about its old location, the old address to the 5, 5, and use the address for 1, 2. That means we have somewhere in memory here a 1, 2. And down here maybe a 5, 5. And this address was used by the player and this by the monster. And everything is fine. But now we change it up so that the monster uses also the 1, 2. And this 5, 5 down here isn't used anymore. Which is a bit of a problem because they both take up space in memory. The 1, 2 is still used, but this 5, 5 isn't used anymore. In fact, we don't even know where it is anymore. There is no way for us to figure out again where we originally stored the 5, 5. That information is gone forever. So now we have this ghost data, just blocking up space in the heap. Now imagine that happens a few times, a few 100 times, a few million times, with data much larger than just 2 integers. Soon the entire heap would be completely filled with data that's not used by anyone, that just blocks up space. And a bit of an issue. So, different languages have different strategies for this kind of thing. If you use something like C, for example, or C++ maybe better, you as a programmer have the responsibility to keep track of these memory parts that you don't need anymore and clean them up yourself. You have to use specific commands to explicitly tell the computer, forget this part of memory, unreserve it, release it into the wilds and let someone else use the memory space. And if you don't do that, that leads to memory leaks, where the computer memory just grows and grows and grows not because you need it anymore, but because the old data isn't freed, and at some point you have an out of memory, because your computer has only finite resources. Then languages like C# use what's called a garbage collector. And this unused data down here, this is garbage. And it collects that garbage. It basically has internally a table that helps it keep track of what memory addresses are still used and which aren't. So it knows that this part of memory has 2 references to it. Some part of our active code still references this specific memory address, so it's safe, we're gonna keep it. This part of the memory down here, well, nobody has any reference to that. Nobody has the address for this part of memory anymore. So no one can use it or free it or do anything with it. And so the garbage collector says, we're gonna free this. We're not gonna release this memory ourselves because no one had put any claim on it, and someone else can use the memory again. Works pretty well, but garbage collection is actually pretty difficult. Because for one, you have to really be careful to keep track of these references. Because there are a lot of different scenarios in where you have a reference or someone else has a reference and you mix them up, or you hide them somewhere, or you have indirect references to indirect references and whatnot. And of course the performance issues, like checking every piece of memory you have and keeping track of what's used and whatnot, that takes a lot of resources. So garbage collection is actually something that can take up a lot of the resources that are not available to your program anymore, because it has to do a lot of calculations. Now, I don't want to scare you away from that, because current generation garbage collection is very optimized. Like, it's very, very good. The first instances of this type of technology, sure, there's a bit of slowness, especially since the computers were also a bit slower. Nowadays, garbage collection is very good. Like, you can use it reliably, that's the most important part, and it's very optimized. And there are a lot of strategies it uses to help optimize the entire workflow. There are things like different generations of garbage collection. So if you really want to optimize your program, if you have something that's very hyper-optimized, actually, I have to say, where you need every little millisecond you can squeeze out, then you have to look into garbage collection a bit more and how it's strategizing and how you can help it organize the memory better. So by giving it signals on what you want to do and maybe use some workarounds, some better memory strategies. But generally, it's more like a fire and forget, especially if you just start out. Garbage collection is going to sort out the memory, keep everything organized, and keep track of all the memory you don't use anymore. Something we don't need to do for the stack, because hopefully for the last time, you always expand downwards as you call methods and then remove the method or the memory space as soon as you return from the methods. So you never have to worry about knowing who owns what. This is actually a different strategy, owning and borrowing. Rust is quite famous for that. Also a different strategy for memory. But yeah, memory management, big topic. Just remember we have the stack, which is pretty simple but very effective and efficient. And we have the heap, which is extremely useful but involves a lot of work, either from you or in case of C# from the computer itself. Now something more. Going back to our player. What if I didn't do this? Actually, let's skip the entire constructor. So if you remember, if I don't provide any constructor method and just have the class written as is, with only the two variables, and now I create a new player, of course without any arguments, because I only use the default constructor, the constructor that's automatically used by the computer if I don't tell it anything else. It will still reserve space on the heap for my player, and it will still give me the reference to that player. But what values does it actually store now? What the computer does, which is doing for both the stack and the heap, when it reserves space, it will clear out the existing memory. So whenever you start out with newly acquired memory, you start out with all zeros. Everything is zero. In both the heap and the stack. And for something like an integer like health, that means, well, yeah, the value 0, that's perfectly fine. With just the number 0. You have to change it to something more usable if you need it, but 0 is a safe number. You can do that. Something like a float, or double, floating point numbers in general. All zeros, that's also usable binary information. It's just the number 0. Still makes sense. Gets a bit more tricky when you go to something like Boolean, which is not a number, but just a state of true or false. But in that case too, the computer knows 0 just means false. Safe. This, however, this is no longer a value, this is an address. Point is now a class, we just changed that. So location here refers to a single number that represents an address in our memory. And address 0 is very special, and that it indicates that there is no address. So the computer knows we are looking at address 0 because everything in memory is pre-initialized with just zeros. And memory 0 doesn't exist. I mean, it sort of exists, but the computer ignores that. And every legitimate address we would get to store a class would be greater than 0. And no, don't think about what actual values would be stored in there. That's not relevant for you in basically ever. Again, I mean, maybe if you make pen testing, or even that. Just don't think about it. Anyway, 0 then means there is no reference. There is no memory address we're referring to. So if I just were to create the player as is now, and were to try to get or change location, for example, let's just skip this part altogether. Let's ignore this. Just say I want to change the location of the player by 2. Before, when point was a struct, well, this was existing memory with two integers, with an integer x that I can change. It might have been 0 because everything was initialized with the 0, but there was a part of memory that I can point to and say that's an integer, increase it by 2. Now the player doesn't have an address for location. We never created a location for the player. The address it points to is 0, which doesn't exist. The computer knows this location points to nothing. There is no memory I can point to and look at that's X. That simply doesn't exist anything. So this would cause an error. That's a null reference exception. Specifically, what happens is here p.location is equal to null, which is another keyword we have to remember. Now, lowercase else. Now for German-speaking folks, and I guess a lot of other languages, this is pretty funny because null is just 0 in German, or null, which is also kind of confusing for us programmers here because when we talk with other programmers and we're talking about null, we sometimes have to clarify, do you mean null or null? It can be funny, but it's subtle. In any case, null just means this location variable stores just zeros. That means it refers to nothing. Null means there is nothing we point to. There is no target memory. And you can't do anything with nothing. Null handling it's useful, but it's also tedious sometimes, and it's frustrating, and it's just, you will learn to hate null reference. And in recent years I've seen more and more effort going into just don't use null anywhere. Ensure that you never have a situation where you have an address, a reference that's null. And if you absolutely need to, at least make sure you program in a way that everybody who uses your code is aware of it and that he can deal with that situation. And actually, this would not, actually this code here specifically, would not be possible in current versions of C#, or at least if you use these settings in a way that I think are the right settings. Because the current version, if the setting is enabled, would simply look at this code and see, hey, location is a reference, point is a class. So this is an address somewhere in memory. But I can create a player with just the default constructor where this location is never set. So we can create exactly this situation where I have a player, a valid player, that doesn't have any location to point to. And that's an issue, because that can cause an exception here. We don't allow that, so the computer will not even allow you to compile your program anymore. Unless you specifically tell it to, yes, I'm aware that this can point to nothing and I'm dealing with that somewhere else in code, please let me do that, in which case it will let you compile. Which it also will do in older versions of C# where the feature is just not available. I still have to write code where nullable is not enabled, where that feature doesn't exist. And I also have to write a lot of code that interacts with systems that have that feature and some that don't. All our new code uses the current versions, so that's not an issue, but we have some legacy systems, so also legacy libraries. That's even more joy. In any case, once you go away from struct and go towards class, there are a couple of things you have to keep in mind, like null. Just be aware of things like that, and don't get frustrated once you start to run into null reference exceptions. If you know what they're about, and if you try to avoid them, null is not as much of a pain in the butt as people make it out. It's not the devil. Though I do avoid it whenever I can. I usually don't have any null issues anymore because I don't use null anymore. Make the problem go away by not addressing it, I guess. So, we had a discussion about Heap. You know what a class is. There's not much left for us to learn until we get to the first actual program. There are maybe 2 or 3 lessons more, which might sound a lot to you now, but trust me, we made a lot of progress. And then we can start programming, and you don't have to watch me awkwardly write things out by hand, except for these little schematics, which I absolutely adore. So I'm going to continue using them. Homework. No? Please come back, please come back. Homework is going to be a bit more freeform. I just want to keep the theme of we have a player structure or class, and a monster structure or class, and a point structure or class, all up to you. And I want you to create additional interactions. It can be whatever you want, but some things I would like is some dash attack, for example, for monsters that ram into the player and then push the player back. That leaves you with some geometry problems to solve. That might be fun. And maybe also health for the monster and a way for the player to attack the monster. And oh yeah, that one's good. Maybe add a range restriction so the monster cannot attack any player. So only if the player is close enough can the monster actually attack the player. Just get some practice and think about different ways you can make use of struct or class, which would be better in which scenario. Maybe try different methods. Maybe try to play around with 2 players and 2 monsters and how they interact, or could interact. Just write some code. Even if you can't retest it yet. Your time will come soon. Well then. That was it for the heap. Thank you for joining in, and I'll see you next time.